Hello, everyone. Yeah. Oh, wow, my mic is way too loud. Hello, everyone. Sorry, I just blew out some eardrums. Apologies for that. Um, we are going to get started today. My cat Stuart is playing very vigorously behind me at the moment. So, today we're going to be talking about concurrency. That is threads in Java. So we're going to talk about threads, the runnable class, and then we'll briefly introduce the idea of race conditions. From there, just some general announcements, and I'll go ahead and pull the slides up here. Homework 5 is going to be out soon. Uh, Homework 5 is going to cover the material we cover this week as well as next Monday. We are going to be talking about concurrency today and Wednesday, and then Friday and Monday we're going to be talking about recursion. From there, we're going to then jump into a bit of introduction into data structures. But so there will be, just a reminder, so this is homework 5, there will be a homework 6 as well. But homework 6 will be the last assignment. Neither homework 5 nor homework 6 build on homework 4 or any previous assignments. They are stand-alone assignments. Additionally, there will be a final exam in this class with a format similar to exam 2. I say similar just to leave myself some wiggle room in case we change things. We hope to have the grades out for the exam relatively soon. Stuart is going kind of crazy back here. You having fun? There's like a 10% chance he knocks over my whiteboard camera. But with that, today we're going to start the unit on concurrency. We're going to talk about how to use multiple threads to execute a program in parallel. And to explain what I mean by parallel programming, the idea is generally, where did all my dry erase markers go? I think cats have knocked them over. Sorry, my house is kind of a mess at the moment. So generally the idea is we have some main thread of execution, and this main thread of execution, hi Stuart. Stuart's very interested in learning today. Please don't knock that over. Thank you for helping, Stuart. All right. So the idea is we have this main thread of execution, and that is going to spark off another thread of execution. And generally, this main thread of execution can create multiple threads. We can have multiple threads running at the same time, and eventually these will change some type of information back on the main thread. Now this is the Stuart, what are you doing? He is just like continuously he wants to we're a cat stream now. Anyway, sorry about that. Sorry about that. All right. So the idea though is we have this main thread, and every time I draw on the board, he decides to attack it. All right, I'm gonna stop playing with my cat during lecture. I swear. Now I should note that this. Oh wow, this marker is not showing up well. I will try to track down my better colored markers. Sorry about that, everyone. So, let me give me one. Where did these go? Huh. I have no clue where my other markers went. All right, well, whatever. Anyway, to that end, I should note that there's actually architecture out now which has no main thread, that the software is built around just concurrent threads, but there's no main thread that receives all the information, and that's actually pretty interesting. If you've heard of the game Doom Eternal, that is implemented with that. But anyway, for now, we're not doing anything so advanced or so modern. We're just starting with the basics of threads. And the reason that we have threads is to improve our efficiency. And I'm going to illustrate this by, and I will upload this code later, but I don't expect that you'll fully understand it. What I have is I have a program that performs a merge sort on a list initially of length 10,000, but then it doubles in size for 10 times in a row. So basically, each run's going to take longer. And if I were to run a merge sort, it's pretty fast, as I've shown before. On a single processor, what you would find is that this program takes, on a single processor, 2 milliseconds for 10,000 elements. But once we get up to, let's see, this is about 10 million elements, it takes 1.4 seconds. But by using parallelization, and we're going to talk about how we do this in a bit, but just to motivate this, let's say I double the number of cores. Instead of 1 core, I use 2. Well, now, you'll notice that instead of taking 1.4 seconds, by using 2 processors, this merge sort only takes 0.7. Takes half the time. If I double the number of processors again, you'll notice that now it doesn't take exactly half the time. It takes a little bit more than half the time, but still, it's faster. The more cores I have, the faster it goes. Up to a limit. My computer has 12 cores, of which one is actually pretty busy running OBS at the moment. You'll see that at 12 cores, I get 363 milliseconds. Not that much faster than I got with 4 cores. Now let's increase this to, I don't know, let's try 100. Well, you'll notice that when I have 100 cores, it really isn't any faster at all. And the reason for this is my processor hardware is limited by the number of logical processors I have. In my case, I have 12. So if I say create more than 12 threads, I don't get any benefit. And the reason for this is that each of these threads that you're seeing runs concurrently, that is at the same time, on a separate processor. So it runs concurrently at the same time on a separate, I should say, logical processor. A standard CPU anymore almost always has multiple cores. 12 is a very common number. So I'm limited by my hardware in terms of parallelization, but the more cores I have, the more, in theory, I can make the process efficient. Now, I should note that this does fall prey to the law of diminishing returns. Why do small arrays get slightly slower when the threads increase? That's a great question. I'm going to answer that briefly. And the short answer is starting up a thread takes time. And so you need to actually be dealing with really large problems to get an advantage. Why does a core have 2 threads? So I have 6 cores with 2 logical processors. It has to do with basically clock cycles. Think of it like it's one logical processor on one clock cycle and it bounces back and forth. And there's certain hardware advantages to that where one is running at a time. Yeah, so you get the law of diminishing returns where each processor you add increases the speed even less. So the larger inputs the smaller inputs do get slower, and that's because managing the threads takes time. And so if you're not dealing with a very, very large problem, you'll often find that threads don't help you at all. But once you start getting into very large problems, threads can help considerably. So I just want to motivate, this is why we do this. Better efficiency. It also enables us to do things like asynchronous development. So I should note that on your homework 4, when you're working with a GUI, every time you hit a button and that fires off an action listener, that action listener is fired off in a thread. And so that thread works in parallel with what we would call the main loop, which is the thing that checks, has a button been pressed yet, has a button been pressed yet, has a button been pressed yet. So now, let's jump back into the slides. So we're going to talk about how to implement threads. We're going to introduce the idea of race conditions later today. We won't actually dig too deep into it, but we want you to be aware it exists, and then we'll talk about how to avoid deadlock using and race conditions using locks and conditions on Wednesday. So first, let's start with how do we run a thread, how do we terminate a thread, and then we'll get into race conditions. So the first thing to note is the formal definition of a thread is a unit of the program or a part of the program that executes independently of the other parts. And by independently, we mean independent not just with respect to on a different processor, but really with respect to time. One of the things that we're going to run into with threads is we know when threads start, but we don't easily know when threads end. We'll talk about that. The idea is the Java virtual machine, which is the thing that simulates a real computer that Java works on, executes each program for a short amount of time, a time slice. We often call this a quantum. I'll write that word here, a quantum. That just means a unit of time. A short unit of time. Let me move my head out of the way here. And I'll just shrink my head a little bit. There we go. And so these time slices or quantums are assigned to different threads. And so the processor will bounce back and forth between different threads as well as different processors in order to try to optimize the program. So this gives the impression of parallel execution. Now I want to be clear. If you're running on a multi-core machine, threads can and often do execute in parallel, but you can still do threads on a single core machine. It will just, instead of actually multitasking, it will appear to multitask by switching programs back and forth very quickly. And in fact, this is how even early operating systems work. They created the illusion of multiprocessing without actually doing multiprocessing. How does it run faster on a single core processor then? What do you mean by it? I don't know what you mean by it. Give me 1 second. Oh, well, how does it run faster than just one singular thread? Well, it doesn't if you have multiple processors. Or so it does if you have multiple processors. So for example, on my computer, I have 12 processors. So large problems run faster when I use threading. But if I only do one thread, they'll run slower. Now, if my computer only had one core, if my processor only had a single core, if using multiple threading would not speed the program up. Do multi-threaded applications run faster? No, not on single core CPUs. All right, yeah, sorry about that. So I don't have a single core computer here to demonstrate this on, but yeah. So JVM is just one CPU. No, it's not. So the JVM is think of it like it's a layer. So at the bottom you have your hardware, and then up the top you have your software, and in the middle you have the JVM, and the JVM creates a consistent interface for the software such that the JVM interface is the same if you're on a PC, Windows, Mac, whatever. But how the JVM interfaces with the hardware depends on the computer. And so if the JVM is on a computer with multiple processors, the JVM will interface with those multiple processors. Is there a limit to how many fake multi-cores you can use? The limit is your memory. So, for instance, I have if you're running on an x86, which is to say a 32-bit machine, your limit is 4 gigabytes. If you can't have more than that. If you're running on an x64 machine, a 64-bit machine, your limit is significantly higher. But it's so my computer I think has 16. What's a fake multi-core? That just means that when, like, let's say I do 100 cores. What that actually means, I want to be very clear. It's not faking any cores. This is just my way of saying how many threads to create. And so if I create 100 threads, but I only have 12 logical processors, at least 88 threads are sitting there doing nothing in memory, waiting on their turn to run. But they're not actually running. So a thread can be running or it can be paused, which is to say it's waiting to run, or it can be finished. So from there, how do we actually create a thread? So the first thing we need to note is that a thread relies in Java on the runnable interface. And the runnable interface has a single method. 99 cores would have the same effect of 1. It is to say that, yeah, it would probably run in the same amount of time because I'd have, again, with 12 cores, I'd have 87 running, or 87 waiting as opposed to 88 waiting. But it really wouldn't run faster. It would just take up more memory. Because the threads do take up memory. So the runnable interface has a single method, and that method is public void run. Takes in no arguments, and it returns nothing. Public void run. And that may seem a bit strange, but we'll talk about why and how we use this just now. So we create a thread by first creating a runnable object, my runnable task. We then create a thread off of that runnable object, and then we actually don't call the run method directly. So let me show a simple example. I have here a simple program that is going to, and this will be uploaded later. What this program is going to do is it's going to print, and I'll just show you how it works, print the time for 10 seconds in a row. And you can see not a particularly exciting program, but it prints the time. So from there, how does this program actually work? And you'll see that we printed 10 seconds from 36 to 45. So the way this program works is we define a thread, a runnable, public class greeting runnable implements runnable. The runnable interface has a single method, and that method is run. But we don't actually call run. So we create our runnable first. Runnable, we pass in hello world, and that's going to be the message that prints. So you'll notice we have this dot greeting. This constructor takes in a greeting. And so, for example, if I were to say spam, let's say I wanted this program to mimic Monty Python. Now it's saying spam each time. This is the message to print every second. And then from there, I create my thread from my runnable. So the runnable I create here, R, is passed into the thread constructor. But you'll notice I don't call the run function. Instead, I call thread.start. And the reason is the Java thread interface handles actually creating a separate thread of execution that can run independent of the rest of the program. To that end, let's say I did something like for int I equals 0, I less than, let's go with a billion, 123, 123, I plus plus, and we're not going to do anything. We're just going to wait a billion and then do system.out.println loop over. The advantage of this, as you will see, actually, this is not. Let me do something in here. Let me do math.square root 10. There's a reason I'm doing that. It's not. Okay, let's do a really slow operation. Hang on, I have too many actually programs running. There we go. Let's do arc cosine uh, 0.8. Arc cosine's nice and slow. See if this works. Okay, arc cosine is too slow. I'm trying to demonstrate something, and I'm doing a bad job of it. Take off a couple zeros here. There we go. So notice the loop ended while the other thread is running. The point being, this is our main thread. This is inside of our main program. This is not running on a separate thread. So the program that creates the runnable, then creates the thread, then starts the thread, then I loop, in this case, 10 million times, and I do some arc cosine, which is a nice slow. This is happening in parallel to the thread that is producing this, print statement. So how do we produce that print statement? Well, I have code here. We'll talk about the try catch block in a second. For now, ignore it. I have code, and what it's going to do is it's for I equals 1, I less than or equal to repetitions, I plus plus, which we do 10 repetitions. It is then going to do system.out.println now, which now being the current date. If you do date now equals new date, that actually just gets the current date time, which you can see here. We print now, and then we print whatever greeting we passed in this case, spam. And then we delay. And this thread.sleep delay, what it does is .sleep takes in a time in milliseconds. So if you pass in 1,000, which we do here, you'll see that that turns into 1 second. So if you'll notice, every time it prints, it's exactly 1 second apart. If I change this to, say, 2,000, you'll see that now everything that prints is 2 seconds apart. So threads.sleep is a way to tell the program wait X amount of time. Now, we'll talk about this exception. It should be noted that anytime you do threads.sleep, it requires this exception, interrupted exception, is a checked exception. So anytime you do threads.sleep, it requires you to handle the interrupted exception. We'll talk more about that in a second. But are there any questions just about, and I'll try to put as much as I can on the screen at a time, any questions about how I created or ran the thread? Because you'll notice once again, I never call this method directly. Rather, I trust t.start to call that method directly. Or call that method indirectly, I should say. Any questions? Sleep is on top of computation time. Correct. Yes. So when you reach thread.sleep, it pauses there until at least 1,000 milliseconds have passed. What's the definition of sleep? It basically means put this thread into memory and don't pull it out of memory and put it on the processor to run until at least 1,000 milliseconds, or at least delay milliseconds have passed. So that's why this now waits, in this case, 2 seconds, because I'm waiting for 2,000 milliseconds to pass, and 2,000 milliseconds is 1 second, or is 2 seconds, excuse me. Stewart, it appears, has calmed down. I know he was, hang on. Sleepy boy, he's taking a nap now. Aw. Stewart is demonstrating how the sleep thread works exactly. Um, he's my buddy. I've had him for almost 10 years now. Um, all right. So with that, are there any other questions about this code before we start adding to this and start kind of complicating a bit? So create an instance of a class that extends runnable, correct? That's step one. Then pass that to a thread, correct? The thread constructor takes in a runnable class. Similar to how the set action listener takes in a an action or a class that extends, or excuse me, implements action listener. So this has to implement runnable, and then we call t.start, and t.start is the thing that calls run. All right, so let's move on to the next example. So now I want to illustrate another and I should note, by the way, now what I want to show is this. Actually, let me move on to this example first. So now here you'll see I create two different threads. I create runnable with hello, and I create runnable with goodbye. Then I create two threads, T1 and T2, and then I start both of those threads. So let's actually run this and see what happens. It's the same runnable, so it prints the time and then it prints the message. But notice right out of the gate, hello does not always print before goodbye. Sometimes goodbye comes first. Usually hello comes first, but not always. You can see goodbye comes first here as well. Okay, we're not doing that in this chat. Nobody, please reach out to that number. That is almost certainly either a scam of some kind or something like that. So, if you wish to reach out to people to study, that's fine. Piazza is a great way to do it. I'm not having phone numbers pasted in the chat because that's just going to cause problems. Because I cannot verify if that number is legitimate or if that is somehow a scam. So I'm not going to have phone numbers or links posted in chat. Thank you. So from there, the point is we don't know actually which thread is going to execute first. We don't know if goodbye or hello is going to execute first. Even though we start one and start two, they execute in parallel and they both execute as quickly as possible. What that means is sometimes thread 1 comes first, sometimes thread 2 comes first after delay. But the point is, they're both running unpredictably. And this is a key point. We cannot predict when a thread is going to finish running. We can tell a thread when to start, but I don't know how many lines of code are going to execute in this program before T1 is done. So we don't know when the thread will finish. We only know when we start it. What type of stuff would lead to variability? I mean, anything could. At any level, we can run into tons of variability. Where the point is, you can never predict what order the threads are going to run in. There's no situation where you can. I mean, there's only variability here. I can't predict what would it's more what type of stuff would lead to predictability, and the answer is not much. You'd have to get into things like join, etc., which we're not going to get into in this class. We will get into semaphores and stuff that add some predictability on Wednesday, but I should note that predictability comes at the cost of reduced efficiency. Why wouldn't it be really predictable? Because the thing is, Java does not decide when the threads run. Your processor decides when the threads run. And your processor is not directly controlled by Java. Java uses it. Is it worth making that trade off in most cases? We'll talk about cases where you have to make that trade off because otherwise your data is going to be useless. And we'll talk about that later today. But for example, if you're accessing the internet, how fast your internet runs is variable. I mean, even if you have the same internet speed in the same house on the same computer, if there's more network traffic going on, your internet's going to be slower than if there's no internet traffic going on. Like that so all of those factors really do come into play. So it's more that you can't predict exactly how long a thread's going to take in any reasonable circumstance. And so you should just like you should expect variability. And we'll get into an example of that here in a bit. Now let's look at actually threads uh, doing something. The first is I'm going to create a thread, and this thread takes in a file. It then opens that file using a scanner. It reads through that file, and it reads word by word looking for a particular word. So for instance, I could do this to say, count the number of times the word Romeo appears in Romeo and Juliet. Or count the number of times dagger appears in Romeo and Juliet. Something like that. Or count the number of times fire appears in Fahrenheit 451. That's the goal here. And so all this does, and it has Sherlock in the name because we're going to do an example with Sherlock, but this works on any text. So here I have the text for The Adventures of Sherlock Holmes, and you can see a lot of different adventures here. It's a pretty big file, and you can download it and read it because it's open source. It's part of the Gutenberg library, so that's why we're using it. And what I'm going to do is I'm going to count the number of times Sherlock appears in the Adventures of Sherlock and Holmes. Count the number of times Watson appears, and count the number of times deduction appears. And the key is I can do all of this in parallel with threads. I create 3 runnables. I create 3 threads. I start all 3 threads. I could also do this with an array. I could do something like word count Sherlock runnable array WCR equals new word count Sherlock runnable, and in this case I need 3 threads, so I'm just going to do 3. And then instead of WCR1, I do WCR0. And WCR1 and WCR2, because I can make an array of this runnable object, same as anything. I could then make an array of threads. Thread T, thread array T equals new thread array size 3. And then instead of creating a new thread, I say thread T0 equals new thread T1 T2. I could also replace this with a for loop. So something like for int I equals 0, I less than t dot length, I plus plus. I can replace this whole thing and say something like, for the sake of simpler code, something like thread, or not thread t, I would say ti equals WCRI new thread WCRI, something like this. And then ti.start. And this would create and start all 3 threads. So I could also do this with an array, is what I'm trying to show. This would also be a fine way to do it. You don't have to start each thread manually. You can create an array of threads. In fact, you often will. And when I run this, you'll see that all 3 programs finish, and they produce the same output every time. But if you'll notice, the order that they finish is different each time. And it's not inherently predictable. You might notice some patterns on my computer, but if you run this on another computer, maybe different patterns emerge. The point is, it's not predictable, so you should not expect it to be predictable. But just once again to show how this thread works, we take in a file name, we take in a target string called find, we then open up the file with a scanner, we loop through the file one word at a time, and then when we're done, we close the file, and if we find the word, we do count plus plus. And I should note this is a contains. This is not an exact match, but rather if you find the partial word in the word. And again, this will all be uploaded later. But so just to be clear, this is the thread class. Notice I'm not creating, or excuse me, this is the runnable class. Notice I'm not creating any threads here. I'm just defining the runnable. And then this is the class where I create the threads from the runnables. What would you do if you wanted to use the exact string? I would change this from contains to dot equals. And in this case, there's a lot fewer Watsons. I guess because a lot of times it's Watson is like followed by punctuation or something. One problem with this is that the word, like for instance, if the text appeared as Watson, this is not equal to Watson. It's just contains. So that's the reason we use contains here. Is it ignores things like punctuation, etc. When we do that. So you can see we have significantly more Watson. So Watson is often followed by a comma or some other punctuation. If you only cared about the count of Sherlock, would it be faster to create 12 threads? They should get the count of a certain section. So this is where it gets tricky. The question you're asking is very good. Regex, by the way, regex is just as fast as doing it manually. Regex is just a formal syntax, but regex does, I think, maybe support some parallelization. I'm not certain. So the question is, can you break the file up into, say, 12 sections and get the sum of each section? You can, but you have to do a lot of work ahead of time to do that, and that's just because file I/O is a bit tricky. When you do file I/O, what you would have to do is figure out the byte length of the file, and then have 12 different starting points, and then read 1/12 of the file. You could do it, but it would take a lot more of using the file reader class. You couldn't really do it with a scanner. You'd need to do it with the file reader class. It would take a lot of work with that. It's totally doable. It's just more than I want to do right now, but it's doable. Yeah. But that's how you would do it. You'd say, okay, let's say the file has 12 megabytes. 1 megabyte is going to be, the first megabyte's going to be one thread, second megabyte's going to be another thread, third megabyte's going to be another thread, etc. Would it make it more efficient? Yeah, if you did threading, it would be faster, provided that you did the file I/O correctly. The thing is that typically when we've done file I/O in this class, we've done it in a fairly limited way. We've just done it from start to finish. And doing it that way multi-threads wouldn't help. Yes, in general, so if the problem can be easily parallelized, then you want to do that. So for example, if I wanted to say blur an image, I could do that in a parallel way. And we'll talk about some examples a bit later. I'm actually blanking on coming up with one right now, and I want to be able to keep moving through this because there's a few other things I want to show today. So first, let's talk about interrupts. So all threads can be interrupted. And the idea of an interrupt is we ask the thread to stop. We ask the thread very politely to stop executing. We cannot tell a thread to stop. We can only ask a thread to stop. The thread can tell us to piss off and not stop and keep going. It's up to how the thread is implemented to decide to stop. But we're going to ask it very nicely. Not that nicely, but I do like that you use the magic word, please. No, we are going to do t.interrupt, but understand this is a polite request. It is not a demand. And what happens is when a thread is interrupted, you can detect it in a couple different ways. The first is if you are sleeping. If a thread is asleep and it gets interrupted, it raises an interrupt exception. If the thread is sleeping when it's interrupted, it raises an interrupted exception. So to illustrate that, when I run this program, I start the thread, I then do t.interrupt, and that causes, because we're waiting here for 1,000 milliseconds, because we're in thread.sleep and an interrupt occurs, it raises the interrupted exception. However, let's say I comment out this line. If I comment out this line, I also have to comment out the catch because it can no longer raise that exception. If I comment out that line, it doesn't like the try either. You'll see that I never interrupted. The thread never interrupted because we never actually got to t.interrupt while this code was still running. But from there, there's also if this dot is there's a way to get the interrupted flag. I'm blanking on it at the moment. It's not within the scope of this class, but there is a way to check the interrupted flag. Let me see if I remembered to put it in the slides this time. But to be clear, interrupt does not cause a thread to terminate. It sets a Boolean variable in the thread data structure. There it is, thread.interrupted. That's what I wanted. If thread.interrupted, this checks whether or not the thread is interrupted. So if the thread is not interrupted, I'm going to say thread has not been interrupted. Else system.out.println 3 thread has been interrupted. And I'm going to do just return, which is to say the thread, I'm politely ending the thread. So if I do this, now because it takes a bit, notice that now when I interrupt the thread, when I call t.interrupt, it has enough time, it goes fast enough that this flag is set before I reach this if statement. But understand this won't always happen. For example, let's say I did, and I'm going to use my for loop from earlier. Let's say I have this same kind of slow for loop here. So remember, this is just a way to mark time. It's a way to waste some time. Now, interrupt will almost certainly we will almost certainly reach this line after this statement has been executed. And because of that, notice that now the program doesn't interrupt, and it's because we don't reach the interrupt in time. That is to say, we've already passed this line of code. What's the reasoning for interrupting a thread? So if you want to tell a thread stop executing, maybe it's I've waited too long. So an example would be, let's say, a timeout. So you're trying to set up a database connection, and you've been trying to set it up for 10 seconds, and after 10 seconds you time out and force the user to re-enter their information. That would be an example of an interrupt. But again, you ask the thread to end. If the user doesn't do something like this, or if in their sleep they don't have an exception that ends the thread, then it's not going to end. But the point is, we want to sometimes, not always, tell a thread to end, But the interrupt doesn't stop the thread. Right. It asks the thread to stop. And if the thread is programmed to stop when it's interrupted, it will stop. But only if it's programmed to stop. If it's not programmed to stop, it will not stop. So that's why the interrupt is a request. So you can guarantee the thread will be interrupted? No, you absolutely cannot. That's the point. The point is you are relying on the developer who wrote the code for the thread to handle interrupts. And if the developer just ignores interrupts, then the interrupt call won't actually do anything. If the code is written correctly, so that's kind of subjective. Because the thing is, there might be a situation where you say, you can't interrupt this. Maybe it's in the middle of some task that cannot be interrupted without having a negative effect on the program's data, where that is to say the data could become corrupted. But generally, yeah, you as a thread developer want to have places where you check, hey, should I interrupt now? If it's a particularly long thread. If it's a thread especially that could take several seconds. All right. So now, we don't have much time left. I'm trying not to go over time just because I know a lot of professors are, and I know your guys' time's valuable. So I will upload all this code, and I encourage you to look at it. The last thing I want to show you is this. And this is I want to preface, this is motivation for Wednesday. So what I have here is I have a class called bank account. Bank account has a balance. I have a deposit function, and I have a withdraw function. I deposit so much money, and I withdraw so much money. Right? Deposit amount, withdraw amount. And then I have a function, get balance. So pretty straightforward, nothing too surprising here. When I create a new bank account, it has balance 0. And then I deposit, I withdraw, and I get. I'm now going to create a deposit runnable. What this is going to do is this is going to take in a bank account, an amount to deposit, an account to tell me how many times to deposit. And this is going to loop count number of times, and it's going to deposit an amount of money into the count and then sleep the thread. So I'm going to deposit money into the count, then I'm going to put the thread to sleep, but I'm going to do this over and over, count number of times. I now have a withdraw runnable. Exactly the same thing, only instead of the deposit function, it calls the withdraw function. And now you'll notice I create, with 100 repetitions, withdraw and deposit. And they both deposit $100 or withdraw $100. So I'm going to deposit $100 100 times and withdraw $100 100 times. Given this, and I'm just going to quickly change this to, let's do 100 threads. So I create 100 different threads that do this. So in total, I'm doing 10,000 times 100 would be 1 million. So I'm doing $1 million of deposits and $1 million of withdrawals. Given that, what should my amount be after I'm done? After the thread is over, how much money should I have? If I deposit $1 million in different increments and withdraw, I should have 0, right? I'm not going to have anything like 0. Actually, that was pretty close. I ended up with negative 200. That's not too bad. Okay, this time negative 1,600. Okay, this time negative 3,500. Okay, this time positive 4,600. Now, this sounds like a bug, and it's because it is. And the reason is as follows. Sorry, I had to fix my camera because, oh, look at how sleepy he is. Aww. So what is happening? what is happening here, and I apologize again for having this green that just does not show up well, but I'm not sure where my other markers went. Is that we have code that says, okay, double balance equals get balance on the account. And I'm writing pseudocode here. I'm not trying to make this exact. This isn't showing up at all, is it? Yeah, that's not showing up at all. Okay. I'll just draw this on the computer screen. All right. So, let's take a look at the deposit runnable. What does this do? It calls deposit, right? So we have two potential, let's say we have two threads running through deposit at the same time. And let's say for the time being that they're running on the same processor to make this simple. Yes, I already said I have multiple processors, but let's say, simple example, two threads running on the same processor. Now again, which thread is running at a given time is unpredictable, but they both have the same account, and let's say, so they both reference the same account in memory, and let's say that account has $1,000 in it, and let's say that these threads are both calling deposit 100. Now, what could very well happen? What could very well happen is this. Because deposit 100 is multiple lines of code, right? What could happen is this thread prints depositing 100. Give me 1 second here. This thread could print deposit 100. It could then say new balance, so it creates a variable called new balance, which is equal to the existing balance, 1,000 plus 100, or 1,100. It could then print the new balance, and then balance equals new balance. And after this thread is over, then T2 says, okay, the new balance is, well, what's the balance? It's 1,100 plus 100. So it prints 1,200. And then balance equals new balance. That could be the order things go in, just top to bottom. But it's also possible that things get a bit chaotic. They're both calling deposit 100. Let's say thread 2 first prints. It then says new balance equals, and it's balance plus amount. So that's going to be 1,100. Balance plus amount. But then let's say this thread pauses. And then thread 1 picks up. So thread 1 prints. And then thread 1 says new balance equals balance plus amount. Well, what is balance? Balance is still 1,000 because we haven't changed new balance, or we haven't changed the balance in thread 2 yet. So now I say new balance equals, and it's 1,100 plus, or it's 100, or 1,000, excuse me, plus 100, so 1,100. Notice these both have the same new balance. Then thread 1 finishes and prints, and then says balance equals 1,100. At this point, our account updates, and this is the balance value. Now thread 2 finishes, prints, balance equals new balance, balance equals 1,100. So we set that to 1,100. So we've deposited twice, but notice we failed to actually save the change of depositing the second $100 group. This problem is called race conditions. Moving my head again. And race conditions are when multiple threads interacting create anomalous, or to say incorrect or unintended behavior. And what we're going to talk about on Wednesday is how we can make sure that threads behave themselves to avoid this type of problem. And we'll start by fixing this code such that it runs correctly. But that's all we have for now. So with that, I will wrap up lecture here, and that will be it. Any questions? Sorry, Stuart was absolutely adorable. He is so... Oh my goodness. This cat is... I had a question about the lab. Is it due tomorrow or next Tuesday? It is due tomorrow. The lab each week is due that week. Hang on here. I'll set up the camera to give us Stewie vision. Oh, there he is. Oh, sorry. There we go. Stuart camera. It's a Stuart stream now. When will we get our Homework 3 grades back? Homework 3 should hopefully be out soon. Homework 4 is going to take a while to grade because it has to be manually graded. We've had issues grading Homework 3 just as everyone else has had issues grading homework because it is due, or it was due right before we went online. For in-class, should we paste the test files into the project root? Correct. Yes, we should. There is an in-class today, by the way. On Colab, it says the due date is next Tuesday. I will fix that. The lab should be due tomorrow night. When I run the code, never terminates. So if you have issues with the in-class activity, jump into office hours. But if it never terminates or prints the word count, what it might be is that you've created an infinite loop in your code. That's possible. So your code never finishes looping. That would be my guess. Maybe your while loop condition never is false, or your for loop doesn't have the incrementation right, something like that. Look at that boy. He's so adorable. Also, I have the color set weird on that, so that way things show up on the whiteboard better. Should the in-class activity word count class implement runnable? It should be implementing runnable. Yes, it should be. How does a computer get drunk? It takes screenshots. That's a great place to end the class. Yes, devious cats. Yeah, so that is... My parents give me, like, little books for Christmas each year, and it's always these little, like, anecdote books, which I enjoy. It's you know, they're usually pretty funny. And that is an apropos book for Stuart to be sitting in front of. And yes, you can see I haven't finished unpacking yet. I still have a box there. For the in-class, should we paste the text files in the project root? Yes, you should. They should be in the project root. Ready Player One. Yeah, I still need to read it. The other one, the books to the left of that, is a novel series by Drew Karpyshyn. The problem is I also have those books that I'm still working on the right. That is the Malazan Book of the Fallen series. And Malazan Book of the Fallen is for people who like Game of Thrones but think it's too simple and doesn't have enough characters or plot lines. That's what Malazan Book of the Fallen is. All right, I'm going to cut it off there. Thank you for watching, everyone. Take care. Have a good afternoon. I will have office hours later today.